Hi everyone, this video is about the Sylow theorems. Earlier in the semester we introduced Lagrange's theorem, which is one of the most important theorems from finite group theory. It says that if you have a finite group G and a subgroup H of G, then the size of H must always divide evenly into the size of G. The question that guides us in our present material is as follows. To what extent does a converse to Lagrange's theorem hold? That is, if we select a divisor M of the size of G, when is it true that G has a subgroup of size M? We'll see over the next couple of slides that the converse of Lagrange's theorem that we discussed on the previous slide holds for every abelian group. So our first theorem here pertains to cyclic groups. And it says, well, if you have a cyclic group of order n, and M is a divisor of n, then that cyclic group must have a unique subgroup of order M. Now, if this result seems familiar to you, it should, because this is a result that we proved back in section 5 when we were talking about cyclic groups. So if X is a generator for G, we can let H be the cyclic subgroup generated by X to the n over M. And then we just use theorem 4.4, where we don't need the extra M there, to obtain that the size of H is just the order of the element X to the n over M, which, as you'll recall from section 4, so this is where theorem 4.4 comes in, that's the order of X divided by the greatest common divisor of the order of X and n over M. And when all the dust settles from that calculation, you wind up with M. So we have produced this subgroup of order M. Now, for the uniqueness, I'm not going to present that here. You can always go back and reread the section on cyclic groups, or you could just take it on as a challenge and do it as an exercise. Now we're able to extend theorem 1, which is about cyclic groups, to a theorem that's true for all abelian groups. So here we're at theorem 2. And we're going to let G be an abelian group of order n, and we're going to suppose that M is some divisor of n. Then G does have a subgroup of order M. Now, just recently, we had this fundamental theorem on finite abelian groups, which says that, that G must be isomorphic to a direct product of these modular integer groups, where all of these p sub i's are prime, but not necessarily distinct, and the size of the group is just the product of all of those prime powers. So if M is a divisor of n, then M is a divisor, of course, of this product of prime powers, which means that M should be representable by a product of those same primes where the exponents on the primes are less than or equal to the original exponents here that we use to form n. So theorem 1, which was about cyclic groups, tells us that each of these modular integer groups has a subgroup H sub I of order p sub I to the s sub I. So now all we need to do is to take all of those subgroups H sub I and perform a direct product. And when we do that, we get this subgroup H of G of order M. So we've just seen that this converse of Lagrange's theorem holds for every abelian group. However, if you have a finite group that's not abelian, the converse of Lagrange's theorem need not hold. And that's the point of the example on this slide. So here we have the alternating group A4, which, as you'll recall, that's the collection of permutations in the symmetric group S4 that are even permutations. So I've listed the elements of A4 right here, and you can see that the order of A4 is equal to 12. In fact, it's exactly half of the order of the symmetric group S4. And what we're going to do is show that it's impossible for A4 to have a subgroup of order 6. So 6 divides evenly into 12, but we're going to show that A4 does not have a subgroup of order 6. So we're going to argue by contradiction. So let's suppose we do have a subgroup H of A4 of order 6. Well, we learned a few weeks ago that there are really only two groups of order 6. There's the cyclic group Z6, and then there's the symmetric group S3. Now, since H is a group of order 6, it must be isomorphic to either Z6 or S3. Now, we can look at the elements of A4 here, and we see that all of the elements in A4 are of order 2 or of order 3. That means there's no element in A4 of order 6, and so we know that H cannot be the cyclic group Z6. So that means that if, that this subgroup, this supposed subgroup H of A4 must be isomorphic to the symmetric group S3. Now remember, S3, of course, like every group, has an identity. It also has 3 elements of order 2. Now, so that means that the identity, E, and these elements here, which are the only 3 elements in A4 of order 2, must be elements of this subgroup H. So this set, K, which consists of the identity and these 3 elements of order 2, must sit within H. And you can check that this K is actually a subgroup of H. In fact, it's isomorphic to Z2 cross Z2. But the problem is that this violates Lagrange's theorem, right? Because the order of K is 4, but the order of H is 6, and 4 does not divide evenly into 6. So the only conclusion we can draw is that no such subgroup H exists. On the previous slide, we saw that there are finite groups for which our desired converse of Lagrange's theorem does not hold. And at that point, we might just think that we should just give up and go away. But it turns out that there is some hope to produce meaningful results along the lines of a converse of Lagrange's theorem. And in order to phrase those results, we need to learn what a p-Sylow subgroup is. So we start with a group, capital G. It's a finite group, and we'll let little p be a prime number, and we may as well assume that p divides the order of the group G. Now, let's suppose that p to the n divides the order of G, but p to the n plus 1 does not. So that means that p to the n is the largest power of p that divides evenly into the order of G. So a subgroup of G of this sort of largest order p to the n is called a p-Sylow subgroup of G. So for example, let G be A4, the alternating group, A4, that we discussed on the previous slide, and we'll let P be equal to 2. So that's a valid value for P, because remember, the order of A4 is 12, and 2 does divide into 12. And in fact, the largest power of 2 that divides into 12 is 4. So if I can find a subgroup of A4 that is of order 4, then that subgroup will be a 2-Sylow subgroup of A4. And in fact, I can find such a thing, right? This subgroup here consisting of E and all of these 3 elements of order 2, that forms a subgroup of A4. And so that is a 2-Sylow subgroup of A4. So at this point, what you might want to do is pause the video and do this exercise, right? So why don't you find a 3 Sylow subgroup and a 2 Sylow subgroup of the symmetric group S3. So here we have what are called the 3 Sylow theorems. So these constitute what we know in the way of a converse to Lagrange's theorem for finite groups. Now you might be wondering, where is this word Sylow coming from? Well, it's the name of a person. So the person is Peter Sylow. And these results that you're looking at here on the screen are from the 1870s. So Sylow was a Norwegian mathematician, and these theorems that he discovered bear his name to this day. All right, so the first Sylow theorem says that, we start with a finite group and we let P be a prime and K a positive integer. So we know then that if P to the K divides the order of G, then G must have a subgroup of order P to the K. So this first part of the first Sylow theorem is highly important. It asserts that, if you're looking at divisors of the order of G that are prime powers, then the converse of Lagrange's theorem will hold. Okay, and then from this first part of the first Sylow theorem, everything else tends to flow. So the second thing says that if you've got a P Sylow subgroup H and K is some subgroup of order P to the K, then K must sit, capital K, must sit within some conjugate of H. Okay, and then on to the second Sylow theorem. All of the P Sylow subgroups are conjugate to each other. So if you have a P Sylow subgroup and I have a P Sylow subgroup, I should be able to obtain mine from yours by some conjugation. So what that means is that if there's only one P Sylow subgroup, then that P Sylow subgroup must be a normal. And then we have the third Sylow theorem, which tells us something about how to count these P Sylow subgroups. It says that the number of P Sylow subgroups of G is the index of the normalizer of H in G. And we'll know that that number has the form 1 plus J times P, so it's always 1 more than some multiple of P. And it must divide evenly into the index of H in G. In the remainder of this video, we do several examples where we show how the Sylow theorems can be used to determine the structure of certain types of groups. Because we will be using the Sylow theorems frequently, it's probably a good idea for you to go back to the previous slide and print it out, or perhaps follow along in the book with the Sylow theorems. Okay, in our first example, we have a group of order PQ, where P and Q are primes, P is less than Q, and P does not divide Q minus 1. So we assert that such a group must be cyclic. All right, well, we know that since P and Q both divide the order of G, that G must possess a P Sylow subgroup of order P, and a Q Sylow subgroup of order Q. This is a result of the first Sylow theorem. Now, the number of Q Sylow subgroups from the third Sylow theorem must have the form 1 plus J times Q, and must divide the index of K and G whenever K is a Q Sylow subgroup. But the order of K is equal to Q, so this index of K in G must be equal to P. So this says that this number of Q Sylow subgroups divides P, which means that 1 plus JQ must divide evenly into P. But Q is bigger than P, and that means that J must be 0. Sorry, this should be a 0. That means J must be 0. So there is a single Q Sylow subgroup K of this group G. Now, the second Sylow theorem tells us that whenever there's a single Q Sylow subgroup, then that thing must be normal. So we know that this single Q Sylow subgroup K must be normal in G. Okay, and now we can address the P Sylow subgroups. So the number of those by the third Sylow theorem must be 1 plus JP, and dividing the index of H in G whenever H is a P Sylow subgroup. But remember, the order of H is equal to P. So that forces this index of H in G to be equal to Q. So putting all this together, we know that this 1 plus JP, that is the number of P Sylow subgroups, must divide Q. So that means that it's either 1 or it's Q, because Q is prime. So the latter equation, that means this one right here, that cannot be true because, remember, we had assumed that P does not divide Q minus 1. So indeed, it must be true that 1 plus J times P equals 1. So there is a single normal P Sylow subgroup H. Okay, we continue on with example 1. So here, remember, we have a group G of order PQ, where P and Q are primes, with P less than Q and P not dividing Q minus 1. We assert that such a group must be cyclic. So what we've determined thus far is that we have a single P Sylow subgroup, and it's normal in G. And we have a single Q Sylow subgroup K that is also normal in G. We know that P and Q are not the same, so we know that H intersect K, remember, which is a subgroup of both H and K. It has to be the identity. Remember, the size of this group must divide both P and Q. P and Q are distinct primes, so the only possibility for the size of H intersect K is 1. Now, what about the size of the group H times K? Well, we have this second isomorphism theorem from a while back. So the second isomorphism theorem tells us that this is the size of H times the size of K divided by the size of H intersect K. But that's P times Q divided by 1, which is equal to P times Q. And lo and behold, that's the size of our group G. And so that means that H times K has to be equal to G itself. So now let's take stock of what we know. We have these two subgroups, H and K, of G. They're both normal. Their intersection is trivial, and their product together is the entire group. And so we had a theorem back a few sections ago that whenever those conditions are in place, that the group must be isomorphic to the direct product of these subgroups. Now, what do we know about H? H is of prime order, and so that means that this is cyclic. K is also of prime order, so that means it is cyclic. And the orders of the two groups, H and K, are relatively prime. So that means that together, the direct product group must also be cyclic. So that says that that's the ball game right there. We have shown that G, which is isomorphic to H, direct product of H and K, must be cyclic. So our next example has to do with what are called simple groups. We say that a group is simple if its only normal subgroups are the trivial subgroup consisting of the identity and the group G itself. In our example, we're going to show that if G is a group of order 351, then G cannot be simple. So we're going to be showing that if G is a group of order 351, it must possess a non-trivial proper normal subgroup. So the first thing we want to do is take 351 and write it as a product of prime powers. So here we can write 351 as 3 cubed times 13. If we apply the third Sylow theorem, we will conclude that the number of 13 Sylow subgroups has this form, 1 plus 13 times j, and must divide 3 cubed, otherwise known as 27. So what are the numbers that satisfy those conditions? Well, the only possible numbers that satisfy both of those conditions are 1 and 27. Now, if there's only one 13 Sylow subgroup, then that subgroup must be normal by the second Sylow theorem, and then we would be done, right? Because we would have shown that G possesses a non-trivial proper normal subgroup. So now, on the other hand, let's suppose that we have 27 distinct 13 Sylow subgroups, right? Since 13 is prime, the only pairwise intersections of these groups can only consist of the identity, right? Otherwise, it would be a violation of Lagrange's theorem. So when you think about that, if pairwise intersections of these 27 subgroups can only consist of the identity, then altogether, these 27 subgroups account for 27 times 12, or 324 sort of non-identity elements, each of which is order 13. So now, once those have been sort of removed from the picture, we know our group has order 351. So there must be then 27 remaining elements. And these must form a subgroup, which in fact is a 3 Sylow subgroup, right? Because 27 is the largest power of 3 that divides the order of the group. Now, there's only room for a single one of those. So that single 3 Sylow subgroup must be normal in G, and that means that even in this case, that G must possess a non-trivial proper normal subgroup. So we conclude that our group is not simple. In our last example, we return to a problem that's sort of similar to the one we did in example 1. So we're going to show that every group of order 255 must be cyclic. So how are we going to do that? Well, of course, we're going to use the Sylow theorems. And the first thing we want to do is to break 255 into a product of primes. So 255 is 3 times 5 times 17. And we're going to let J, H, and K be 3 Sylow, 5 Sylow, and 17 Sylow subgroups of G, respectively. So if all of those subgroups are normal in G, then G will be isomorphic to J, direct product of J and H and K. This is by exercise 15.4. Now, all of these groups, J, H, and K, are cyclic because they each have prime order. And further, because these primes are distinct, that means the orders of J, H, and K are pairwise relatively prime. It follows from the results in section 6 that the group G itself must be cyclic. So to finish the whole problem, what we want to do is show that there is a single P-Sylow subgroup for each prime P equaling 3, 5, and 17. So remember, if there's a single one, then it must be normal. That's by the second Sylow theorem. Okay, now we can use the third Sylow theorem to get conditions on the numbers of these P-Sylow subgroups. So the number of 3 Sylow subgroups has the form 1 plus 3j and divides 85. And what that means, if you examine this for a little bit, you'll see that this means that there is only one 3 Sylow subgroup. And so we're in good shape for J, right? J then, which is our 3 Sylow subgroup that we've been given, that must be normal, right? So we're in good shape for 3 Sylow subgroups. For 17 Sylow subgroups, it's the same sort of thing. We look at the third Sylow theorem. It gives us these conditions on the number of 17 Sylow subgroups. And again, we can analyze this and we can find that there's only one. So for K, we're in good shape. Now the problem emerges when we look at the 5 Sylow subgroups. If we look at numbers that are of the form 1 plus 5j and divide 51, we see that there could be 1, which would be great for us, or there could be 51. Right? So it's a distinct possibility right now that we could have 51 5 Sylow subgroups. And what we want to do now is to show that really we can't have 51. In fact, we must only have one 5 Sylow subgroup. So here we carry on with example 3, where we're trying to show that every group of order 255 is cyclic. So we had decided that really what this boils down to is an analysis of the 3 Sylow subgroups, the 5 Sylow subgroups, and the 17 Sylow subgroups. We showed that there's a single 3 Sylow subgroup and there's a single 17 Sylow subgroup. And now if we can just show that there's a single 5 Sylow subgroup, then we're going to be done. Now remember that H is a 5 Sylow subgroup. And K is a 17 Sylow subgroup. All right, so notice that if we take the group HK, that is a subgroup of G, and it turns out that's because K is normal in G. That's, I think, from an exercise back in section 11. And further, if we want the size of H times K, we can use the second isomorphism theorem to get that its size is going to be the size of H times the size of K divided by the size of the intersection. But because H and K are of prime size and those primes are distinct, we know that the size of the intersection just has to be 1. Okay, so the size of the subgroup HK is 85, or 5 times 17. Now notice that this group HK, it is of order PQ, where P is less than Q and P does not divide Q minus 1. So we can apply example 1 to know that this subgroup HK is cyclic. And so what that means is that HK is cyclic, and hence it must be abelian, right? So that means that H, being a subgroup of an abelian group, must be a normal subgroup of that group. And meanwhile, HK is contained in the normalizer of H in G, which is the largest subgroup of G in which H is a normal subgroup. So now we can set up some arithmetic involving group indices, right? Well, if I look at the index of HK in G, I can obtain that just by taking the order of G divided by the order of HK. That's equal to 3. But that index here is the product of these two indices, where the first one from the third Sylow theorem is the number of 5 Sylow subgroups, and the second one is just, some number, right? So what we are requiring now is that the number of 5 Sylow subgroups, which must have this form, must also be a divisor of 3. And the only way that that can happen is if J is 0, so that there is a single 5 Sylow subgroup. And that concludes the result.